Hi, Nancy.
We are live. Live, I
We
tell you.
did it.
We live. It's
What's happening?
Halloween month.
Okay, I got all the pieces that I need.
Yeah.
What's happening? Man, it's weird. So we do a discussion club on our Discord server every week. I was just like, it's been quiet, except for Tess being in safe mode. Like, is it just that we've been so overwhelmed by all of the space news that now things are just kind of quiet?
No, we actually had on Tuesday with the Daily Space team this moment of, because Monday we'd been like freaking out trying to find enough content to fill 22 minutes. And
Yeah.
there were a whole lot of rocket launches and a whole lot of nothing else. And the issue I think that we're starting to see is this tapering down of what people had left to publish from the before times, the reduction in what people were able to accomplish during the pandemic. And we're just at a point where everyone is tired. Everything we had that was easy is used up, and who has the energy for the hard stuff? Yeah.
I'm going to disagree. Like, it really feels like a volume change. That's all. It just feels like normally there's this much, and this week there's been this much, which has been nice because that's where I can see again.
Right, but last week was like a normal amount and it was DPS. We should have died last week by science news.
So did we? Yeah.
Yeah, so like last week was a normal volume of science news.
Yeah, there wasn't a lot of special,
and it was
of
DPS.
special info coming out. Yeah.
And this week is GSA, which
Right.
isn't
Which should
exactly a
still
minor
be.
event for the science community.
Yeah. Yeah, it's like when the AAS meetings happen. It's overwhelming. It's just bottomless. Yeah. Yeah, I don't know. It's just it just feels quiet. Too quiet.
Yeah, I agree.
But I'm fine with it.
Look, someone told us to hold our breath until the SLS
definite
launches.
hold. Are we still holding? Are we live?
We should be live. Do you need to press something in the background of YouTube?
No, it says I can end the stream. You've been live for 13 minutes, but I don't think we're live.
I see us on Twitch.
There we go. Okay, some people mentioned. Okay, so Nancy's live. So if Nancy says live, then we're live.
All right.
Yeah, there we go. They see and hear us. You got to confirm our existence. This is a jittery, rickety internet system made of duct tape and baling wire. It never works. We have no idea whether anything is functioning. We exist only when you observe us.
It sometimes works.
But sometimes might as well be never. Like that's intermittent. Intermittent problems are the worst kinds of problems.
Yeah, that is entirely true.
Yeah.
I'm trying to figure out whether it's channeling Heisenberg or Schrodinger with this comparison.
Yeah. Cool. All right, well, let's just do it. Whatever. Okay. Let's do this live.
Pressing record.
You are? For what?
We record this so that if YouTube burps, we have something.
That makes sense.
I am your backup.
I just figured
you were. Know this.
I just figured you were like in astronomy cast mode, astronomy cast brain.
No, I do this every week, and only Nancy and I were aware until now.
Oh, good. Backup top of backups. That's a good thing. It's funny, like when I do an interview now, I record my video, I record their video, audio. I record the Zoom meeting. I record my audio, and then I record one more backup of the video and the audio.
But that means you can like remix it however you want.
Well, that's exactly it. Yeah, I've got a nice full version of my audio, a nice full version of their audio, etc., and then we can mix it however we want. All right, let's go. Hello and welcome to the Weekly Space Hangout for Wednesday, October 12th, 2022. I'm Fraser Kane, the publisher of Universe Today. This week, we're going to be talking about DART success. Hot gas swirling around the supermassive black hole. A bizarre, very cool nebula. Dinosaurs surfing on the biggest wave. Lowering the cost of orbit. Reusable rockets. And asteroid classification, shock darkening. What is it? How does it form? Why does it matter? You can tell Nick's here today. Joining me this week, we've got Alan Versfeld. Hey, Alan.
Fraser, how are you doing?
Well,
good to be here again.
I'm doing very well. Good to see you again. And again, you are a trooper. It is some horrible time in the morning, so thank you so much for joining us.
Yeah, it's dark outside.
We've got Dr. Nick Castle. Hey, Nick.
Hey, Fraser. How's it going?
Oh, I muted you. Can I unmute you? There we go. All right.
We're here.
Hi, Dr. Nick.
Hey, everybody.
I see. I muted you just for me, but I didn't mute you for everybody. I pressed the mute button.
That won't be confusing
and so only I could not hear you. Like la la la. I'm not listening to the background hiss hum.
So it's a normal week.
Just like it just put you on mute and just go on with my evening. No, man, you have important things to say, and we're going to get into it. And finally, last but not least, we've got Dr. Pamela Gay. I can't believe I almost messed that up. I think maybe another 650 practice sessions of me saying Dr. Pamela Gay. I'll get the hang of it. Hey, Pamela.
Soon enough.
Normally,
I am doing well. I suspect that was going to be the question you were going to ask before I confused your train of thought.
Now, you are always sort of here with us in spirit, in that you're engineering the show every week, but you're actually now on camera this week to share the news, the good news about space.
I am. There's a variable star, therefore I needed to be here.
Right. You did your doctoral on variable stars, right?
Master's thesis, but yeah.
Right, your master's thesis. Right.
I went out and did galaxies later.
Those things. Okay, yeah. So before we get into, it's just news, no guests this week, but before we get into the news, I want to give a huge shout out to our good friends and fans at the Weekly Space Hangout crew. You can go there, join them, go to wshcrew.space. It's an amazing community. You can chat. You can get your executive producer privileges for running the show, and then you can just invite guests to the show. Take some of the load off Nancy Graziano. That's the key. All right, let's get on to this week's episode. Alan, the big story, DART success.
Yes, I don't know if you've heard about DART. I might have mentioned it once or twice, and I think everybody in the world is talking about it today and yesterday. I'll cut straight to it. It worked. It worked really well. They were hoping that they would change the orbit between Didymos and Dimorphos they were hoping up to 73 seconds. And instead they got a full, now I've blanked out. 30 minutes.
32 seconds.
33 seconds.
Oh, sorry, yeah. 32 minutes, rather.
Minutes, yes.
32 minutes. Yes.
Yeah.
So it just shy of 12 hours for an orbital period to 11 and a half.
Yeah.
Yeah. So really, I think that was better than even the best models they'd hoped for, wasn't it? It was quite a good, very effective result. So there's lots of triumphant, we did it, we've moved an asteroid announcements all over social media. It's very exciting.
Yeah, the dinosaurs were truly avenged.
Yeah.
With that kind of a change in orbit. Like if it was 75 seconds, I think the dinosaurs would have been looking down on us, disappointed, and said, "Is that the best you can do?" But
yeah, I mean, it would have been
great for us.
I was going to say it would have been great if
next time we send a bigger
pieces, but yeah.
Yeah, well, next time we send a bigger spaceship. The point is for them to have beat their hopes. By a factor of 60, 30 to like they were hoping for 30 seconds and they got 30 minutes.
Yeah, that's pretty good.
That's big.
Yeah. Mm. I'm fascinated by the tail.
What are the possibilities? Yeah, why don't you talk about that tail, Alan? What happened?
Well, I'd love to know. I mean, it's got a tail. It's a comet. It's this lovely split tail extending for this huge distance. I mean, I'm not a rocks in space guy, so I rather naively would have thought it would just be a big bursting cloud spraying out, like those images I was talking about the last time I was on here, with the ground-based telescopes were showing in the minutes after the collision. It was almost a hemispherical cloud spreading out, and now we've got this long, beautiful, straight tail. What's shaped it? I'd love to know that.
So it's like a comet, and so you've got the light pressure coming from the sun that is impacting the particles. So when DART hit the asteroid, as you said, it smashed out this big cloud of debris, which has really interesting shape, very similar to a comet. Oh, sorry, a crater on the moon. The rays coming off of a crater on the moon, and within 2 days, that tail was 10,000 kilometers long, and within about 5 days, it was about 50,000 kilometers long. And you've got this, it's just like a comet. Just the light from the sun is blasting away these particles into this long, thin tail. And eventually it'll clear it up. The thing that was kind of interesting that made the interpretation a little more difficult was because of the amount of debris in the tail and stuff. That made it harder to actually measure the position of the asteroid after the impact, and so it took them a little longer to be able to actually get a clear view to it. Nick,
I was also just going to say, what's confusing about these tails is with a comet, we think about it being mostly gas and really fine dust. Here we hit a rock. We didn't hit an icy body; we hit a rocky body. So I don't think we'd really anticipated that the debris would turn into a tail instead of just falling back to the body or being absorbed by the parent. I mean, I think worst case scenario, we'd figured it would make a ring. Nope.
apparently you're muted, Pamela. Pamela, you're muted. You specifically are muted.
I can still hear her.
Mm-hmm.
Yeah.
All right. So as I was saying, one of the things that has happened as an astronomer hanging out with all of you planetary science folks is I don't go into stories like this with a lot of preconceived notions, but I do go into it with the voices of all of you in my head telling me over and over and over that there's no such thing as a truly rocky body, that everything is a mix of rocks and ice. And at Bennu, there were ices. At Ryugu, there were ices. And in this particular case, just like L-Cross slamming into the moon, there were new things revealed and exposed to sunlight that weren't exposed to sunlight before. And if there's any ices in there, it's now going to be going, woohoo, sunlight, and forming a tail as it jets from this object that had it previously trapped like a genie in a bottle.
But that's a lot of ices to do that. That's
And
where
I'm
I'm
okay
kind
with
of
that.
gobsmacked with it.
And
Just
I'm
saying,
an astronomer.
And I study metals in your world.
Yeah.
Right. Yeah. Yeah. Everything's a metal. That's funny. But yeah, so I mean, I guess people are wondering what comes next. Do you think, Alan? What's the future now? Next step?
So this is the only object. Well, that's not true. We smashed into other objects before, but this is the only time we've tried actively to redirect something and had a measurable change in velocity. So this needs to be repeated on other objects because they're not all the same. They're all going to react the same way. Like for example, the tail here, I've seen mention that the ejection of the tail might even have thrown a bit of reaction mass, actually almost boosted that velocity change. Will this happen again? We need to improve our spotting of asteroids because there's still more out there. Because obviously, this doesn't help if we spot the asteroid a week before impact. We need information. We need to be able to launch a mission in time. So yeah, that's the two big steps. This is just step. We know we can do it. Now we need to verify. Will it work the same every time? And make sure that we can do it when we need to.
Yeah. And then you were mentioning Hera, Pamela. What's that?
Hera is a European Space Agency mission that is going to go and spend several years flying along with Dimorphos and sorry, my dogs are in the background. Apologies, everyone. Is going to be flying along with these two binary asteroids and getting detailed images to send back to us. It's one of these unfortunate situations where they weren't able to get it launched in time to get there for this event, but it's going to allow us to see the long-term evolution of the system.
All right, let's move on. Now, Pamela, let's talk about this nebula.
Alrighty, so this is one that was first brought to my attention by the ever amazing work of Judy Schmidt. She is just regular, everyday human who has not gotten a PhD in astronomy and has instead become amazing at processing images in some of the most artistic of ways. And when she first saw these images hit the server, she put together a quick processing here, which shows all the diffraction spikes and shows that how JWST was slowly rotating between the different exposures, creating these multiple versions of the diffraction spikes.
Oh, I never noticed that.
Isn't
Okay.
that cool?
Yeah.
And so then the JWST team processed everything into this beautiful image that allows us to really just focus in on these bands of light that appear around a central star. In this case, the star is actually two stars. It's one of those weird things where binary stars in some areas of the sky dominate, but we refer to this entire system as WR 140. This is an OB type star and a Wolf-Rayet star that have a 7.9 year orbit around one another. And it turns out that one of the side effects of this orbit is they are sending out these rings every 7.9 years of dust. And so we are looking back at over 100 years of dust formation in this particular system. We'd already known that this was going on to a certain degree from other telescopes, but with JWST, we're getting more and more detailed results. And this was one of the projects that Well, when they were doing this one, they were still able to get MIRI data out of JWST. And so they were able to look at it and get us temperature information, get us spectral information. And this is building up those detailed pictures of just what is possible when stars are shedding material in binary systems that we'd hoped to get with Hubble. And we are finally getting with JWST.
So if I could get closer to this system and I had the ability to take long exposure images,
yes,
what would I see?
If you got sufficiently close enough, you would see two truly massive stars that make our sun look like the Earth next to Jupiter, pretty much. And each of these stars are giving off basically puffs of their outer... They have solar winds, stellar winds, that are carrying with them a variety of different particles. But up close to the stars, it's not yet dust. It's just particles streaming away from the stars. Now, in the process of these two objects swinging around one another, these particles are mixing in just the right kind of environment that you have dust formation taking place. And so you will get, with one orbital swing, a shell of dust. With the next orbital swing, a shell of dust. This isn't a spiral. These are nested shells. Now, this is just the highest density parts that we're seeing. We don't really understand just how low a density the dust gets between these shells, but it's still a really amazing process where it's the interactions of the system that allows the dust formation to take place the way that it does.
That's really cool. So, interesting note, I'm interviewing Judy on my YouTube channel a week from now. Yeah, we've hung out a lot before, and she used to do a bunch of imaging processing for Universe Today, actually, and then has just grown way beyond us. But we maintain contact, and so we're going to do a follow-up interview, and I plan to just have her spill the beans, like how, and also how do you do this? What are your tools? What are your techniques? Where are you finding the raw data? How do you approach this? How can other people follow in your footsteps? Because the thing that Judy figured out is that there is just these vast, unmined repositories of incredible images that people have never even seen. Just the astronomers gather their... He's like, wait. She is...
This until I saw it on her Flickr page. And this doesn't even really like give you... I'm failing to be able to scroll. This doesn't even really give you full justice on how amazing this image is.
Yeah.
And why has no one else ever shown this to me before?
Yeah. What's the picture? What took it?
Let me go backwards.
But even like that, those first pictures of Jupiter, when we saw them from Webb, I don't know what you guys thought, but I was like, meh. Yeah. It's kind of like overblown, and then Judy got her hands on it, and you're like, okay, yeah, that's amazing, right? That's so good.
This was from EMM.
She's a wonder.
I don't know what EMM is. Oh, the Emirates mission, Mars mission.
Okay, the Hope mission.
Yeah.
That's amazing. That's really cool. Yeah, she's the best. Okay. Let's move on. Nick. Let's talk about reusable second stage rockets.
Yeah. So a story that caught my eye just kind of got my brain going a little bit. And so this whole rocket revolution we're going through, where the cost to orbit is coming down, is because different companies said, all right, how do we approach the problem of reusing rockets? And SpaceX has been a clear leader in this, but their fundamental decision was, let's take one really big engine and turn it into 9 much smaller engines. Because the bigger your engine is, the more wear it has. It's just simple. Well, not simple, but it's just physics. It's the hotter your exhaust is, the more you're pumping through, the more you're going to ablate material out of that engine, the harder it's going to be to service. And so they made them smaller. Well, SpaceX has gone on to do a lot with that, where now we routinely see amazing videos of these rockets coming back down and landing. They've even worked on catching the fairings. That is the stuff that encases satellites as it goes up. And, how many parts can we reuse? But the thing we notably don't see is second stage rockets being reused.
Mm-hmm.
And there's some good reasons for that. The first stage rocket gets you up out of the atmosphere. Second stage rocket gets you up to orbital velocity. So by the time it's done its job, it's in orbit. These guys are working with the concept of, well, we want to make the whole thing reusable, every last piece. And one of their big accomplishments has been looking at how do we make a second stage rocket design that incorporates some of these same thought processes of how do we make it serviceable, reusable, and get it back to the ground. This is Stoke Space, which was originally founded, as I understand it, by 2 guys and is now up to a staff of about 76 or so. And this is their demonstration of their concept for a second stage rocket. It's running 15 of their engines. I believe the full model is supposed to have 22, something like that. But what they've done is instead of the traditional one big bell nozzle on your second stage, they made it a ring of much smaller ones. And the reason why they made it a ring is because they want them all to work in concert to make one stream coming out of the back of the rocket. Right. So one of the big problems with the second stage is that bell is made delicate. To operate in space, it doesn't ever have to worry about atmosphere unless you want it to come back. So you can either make those a lot heavier, which is a problem because it's more mass, and that's everyone's worst nightmare when you're going to space, or you can build a ton of shielding. They said, let's just move this a little bit higher into the rocket, use smaller engines, and have them work together in concert to have these small pieces make a stream. The test firing is amazing to watch. I highly recommend it. This is just a one-frame capture from their video. But yeah, that's basically the story.
So, I mean, we've seen a couple of companies, like obviously the most famous one is SpaceX, who they are considering developing a fully reusable 2-stage rocket. And actually the Starship Super Heavy stack is on the launch pad. The plan is that, Starship is the size that it is because that's like the minimum size that's required to be able to have to retrieve the upper stage. So do we know how big their upper stage rocket they're planning to make?
If I remember right, the number they cited is 1.65 tons is how much mass it can lift to orbit. So it's not small, but it's not as large as something like Starship.
Yeah, that's tiny. Like 1 ton versus 100 tons to orbit.
Yeah. I mean, the thing about Starship is it's huge. It's meant to take a large crew or a very large cargo and send it long distances. I mean, that's Musk's scope for it is saying, let's send this to Mars. And they built that from the ground up with that in mind. These guys are saying, well, let's just do normal routine rocket business, in Earth orbit, geosynchronous, LEO, etc. But let's bring that second stage back.
Yeah. As you say, that the job of the second stage, the upper stage, is to give the rocket that kick so that now the payload is going 28,000 kilometers per hour. Therefore, the second stage is going 28,000 kilometers per hour and has to now enter the Earth's atmosphere. And we've seen what happened. You see when the space shuttle was coming back through the atmosphere, how hot it was getting, the capsules from the Soyuz and so on. You've got to make a thing that was never designed to go that fast, never to go through the atmosphere like an upper stage, be able to do that and safely, successfully land. So, the key to their architecture that's going to make it different from, like, is it parachutes? Is it powered landing? What's their way?
Well, the main thing they're publishing about is their engine design, and that's this annulus design instead of a single engine, because this annulus they could embed in the body of the rocket. The heat shielding that you'd have to ingrain in the rocket will protect those engines without having to add a whole bunch of extra layers. Right. And that they're using that annulus means that they can essentially simulate a much larger engine with how they're doing their design without having to actually use a huge engine.
Yeah, I mean, from what I saw, they're going to have like a whole bunch of little nozzles that give you the equivalent of that much bigger Bell nozzle, the vacuum nozzle, but still have something that's a lot more rugged. And you can see that would be glad to come back through the Earth's atmosphere, probably.
We hope.
With a little more hardening.
Yeah.
And yet, so it's like a ring. That's really interesting. It's a really cool design.
It is. It's very different from what anyone else is talking about.
Yeah.
I'm really hoping this works, because it'd be very cool to see a completely reusable launch stack with just a wildly different concept than things like, a space plane or the space shuttle, or for that matter, even Starship, which is drawing a lot of its heritage in terms of the idea of how it would work from things like the space shuttle. This is just totally different.
Yeah, yeah. I mean, it is interesting that, like, once SpaceX said we're going to try and figure out how to make a fully reusable rocket system, other people have come out of the, into the conversation, and you've got Rocket Lab's plan with their vehicle that essentially the upper stage is to the fairing, and is going to be able to release the payload and be able to re-enter. And then you've got the I forget what it's called. The European Space Agency is building their one that kind of looks like a little mini Starship, and same thing. It's sort of like a Crew Dragon, but it also is able to it keeps the trunk. Well, Dragon dumps the trunk into the atmosphere. This will keep the trunk, but it'll still need an upper stage. So you've got all these different ideas, and of course, what ULA is doing, they're building with the Vulcan. They're saying, well, the engines are the most expensive part. Everything else is just a tube of metal. If we can save those engines, then we can put them back on a new rocket and save money. So it's pretty fascinating. Not to mention, there's probably, I know of like 4 or 5 companies in China that are approaching various levels of reusability, from Falcon 9 level to Starship level. So you'd be crazy not to be investigating the technology of reusable rockets. Or you go the spin launch way, and you don't even need to have a rocket. Although,
you don't have a rocket. You just have a high energy source propelling things up from the ground.
Yeah, you just throw things into space, and you save yourself.
One of the things I love is when you get enough different engineering groups approaching the problem. Some of the ideas will be crazy. Just like some of them will be nuts.
Yep.
But they'll try them, and we'll learn something, and that'll make progress moving forward.
Yeah.
I mean, if you go back to the original space race and say, we're going to bring the whole rocket back, Wernher von Braun is going to laugh his butt off at you and say, no, you're not.
You can't. Yeah. It is interesting to me, like, just how much we're seeing. Like, when you look at what's happening with, say, the Space Launch System, it is Wernher von Braun's rocket. He would get the Space Launch System, but as you say, right, and so,
although he'd probably say, why hydrogen? Why?
Yes, that is true. Yeah,
and especially since his team was notorious for drinking a wee bit of their rocket fuel. I mean, there's so many reasons not to use hydrogen, and that is the most amusing.
Wait, don't you want it? Like, if your rocket fuel is hydrogen and oxygen producing water, then you could drink that. But you don't want to drink kerosene.
They didn't use just kerosene.
Did they have kerosene for the Saturn V?
So some of their early rockets were more alcoholic-based fuels.
Oh, I see. Wood alcohol, possibly. Yeah. Yeah. Don't drink your rocket fuel. All right, let's move on. But that's really cool. I had never even heard about this. It's weird because I usually follow everything that Eric Berger reports on, and I had missed this one. So nice job, Nick. You surprised me. Alan, let's talk about a hot gas bubble swirling around the Milky Way supermassive black hole.
Yeah, so I first saw this headline, I almost passed over it because we've seen a few announcements like this over, wow, the last 10 plus years. Areas of gas or stars moving close in and they're orbiting very quickly. This one is quite interesting because it's just the sheer speed of the thing. It's a hot region of gas orbiting the supermassive black hole at the center of the Milky Way at a distance about the same as Mercury orbiting the Sun, and it's moving at a speed of about 30% of the speed of light. It is extraordinarily fast, just this massively quick orbit. And this was detected with the Event Horizon Telescope. Remember the one that produced those stunning images of the core of M7, and then about a year or so later, the Milky Way. We got those great, lovely close-up images showing that distorted ring structure. So while doing those observations, they were using the Atacama Large Millimeter Array to provide calibration data, simultaneous observations, and they spotted a flare in X-ray, which is usually associated with these hot regions orbiting the black hole. Apparently, it's something to do with magnetic effects interacting with that hot gas, which generates these bursts of energy. But this time, they also often pick it up in red as well. But this time, it was seen in radio. Elmer saw it as well. So that's quite an interesting extra insight as to just what's going on around the black hole. Not a lot of detail yet, but I thought that was interesting. Yeah.
So what is it? Do we know what it is that's going around?
They're rather vague about that. Probably just a region of hot gas, just some material that's yeah.
From what I remember, this thing is orbiting at the orbit of Mercury, which is pretty close, and it's just taking a few hours to go around the black hole, and so it's moving at about 70% the speed of light. 30% the speed of light. 30% the speed of light. Fast.
70 minutes, 30%. Yeah.
There you go. Yeah, 17 minutes, 30% the speed of light, which is, I mean, it's mental, right? Like things to orbit black hole, like those are so extreme. Yeah. And I mean, you're totally right. Like we've seen blobs go around the black hole before, and we've even detected little gamma ray bursts. I remember there was a burst of gamma ray, not a gamma ray burst, but there was one that was 3 times the mass of the Earth, and it let out enough gamma radiation for us to detect it, no problem. So anytime that black hole feeds, we see it. And this is future food.
I can't help but think just the kind of velocities we reach in a particle accelerator are orders of magnitude slower than this, even though they're extremely high energies. Like a few hydrogen atoms just running into that cloud would create a massive amount of energy release. Like that's crazy to think about.
Well, I mean, this in CERN, I mean, they're running them 99 point blah 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 C. Like they're fast. The trick is it's one proton.
It's still amazing to imagine that these systems are casually experiencing the production of molecule or the production of atoms that are highly unstable, of things like the Higgs boson, pentaquarks. They're just coming in and out of existence, whereas here we have entire careers dedicated to creating one or two of the things that happen per moment in this kind of a system.
Yeah. So the LHC is 99 point 999999991% the speed of light.
Okay, stand corrected. The LHC is about 3 times as fast.
yeah, but it's a proton as opposed to a blob of gas that is significantly heavier than the Earth, going at 30% the speed of light. Yeah,
I find that this gas cloud and things like it, they help me to understand some of the ideas that we throw around when we're talking about black holes, like the idea of spaghettification, right? Something that falls in, they get stretched out by tidal forces. And there was that short story that Larry Niven wrote way back. I think it was his first published story, I think, called Neutron Star, where somebody has to work out why people orbiting this new neutron star keep vanishing. And he basically finds that the tidal forces are enough that objects in the far end of the spaceship get flung away, and obviously in the near end get sucked in, and you actually sit right in the middle. It's a lovely story. It illustrates the tidal concepts behind all of this, and it's all very abstract and very exciting and very fictional. And then you come back to this story and you think, there it is. That's it. It's traveling at a, I mean, Mercury's orbit is what, 88 million kilometers, thereabouts?
Yeah.
And it's whipping that circle. So, well, that times pi is, times 2. That distance in 70 minutes, doing a full circle. I get it now. I really, really feel it now. Now I know what they're talking about.
I just need to point out that Fraser often teases me, and this will happen later in this episode, for being giddy at death and destruction, and you just referred to a spacecraft that is launching people in and out of a spacecraft as very pleasing. And I need this book in my life.
That's funny.
I believe it's. I think you can find it online, actually. But anyway,
yeah, I love those Larry Niven short stories. Weak on character, great on concept. I mean, that's Larry Niven's bread and butter, is to go, what if a microscopic black hole fell into the moon? And the story is a bunch of astronauts arrive on the moon. They find an ancient laboratory, and they see a weird little black hole being held in this electromagnetic field, and they accidentally turn off the field, and the black hole just drops into the moon. And they're like, "Huh, is this a problem?" And they do the math, and yes, it turns out it is a problem. So, really good.
For a frame of reference, I just want to point out Mercury's orbit takes it almost 90 days. So this is stupidly fast.
Yeah. That's funny. Wow. Okay, let's move on. I choose Dinosaurs and a Gigantic Wave.
I said the death and destruction was going to be coming later in this episode.
Right.
So I understand that this may not seem like astronomy to begin with, but you need to understand that just as every 5-year-old loved either dinosaurs or astronomy, I too love dinosaurs and astronomy. And since it was an asteroid that killed the dinosaurs, I maintain that astronomy won. But I still love the dinosaurs that were killed brutally, terribly, by an 8.7 mile across asteroid traveling at 27,000 miles per hour. Now, for those of you that use more civilized units, that's 14 kilometers across, or 43,500 kilometers per hour. Now, that's only one of the confirmed asteroids. There is now evidence for a sub-ocean crater that dates back to the same period of time off the coast of Africa. So there may have actually been multiple parts of the same object, or two that were traveling together, that whacked into our world and created, along with the Yucatan Peninsula, the KT boundary of iridium that covers our planet. And we are now getting
KPG.
evidence. Shush. We are now getting evidence that this event triggered a tsunami that was multiple kilometers tall at its peak and was like a ring radiating through the world's oceans, and it traveled outwards. This particular map, red is the high points. This is 4 hours after the collision. 24 hours after the collision, these expanding waves were zeroing in on what is now the Indian Ocean, where they crossed a little more than 24 hours after impact. So we have something that you can't experience on our world anymore. We had rings from the same splash traveling outward, and they crossed. And roughly 48 hours later, they began to converge back in on what is now the Gulf of Mexico. Now, this tsunami alone is amazing to think about. And one of the things that stood out to me about this paper is the researchers openly admit they did not try and model how much seawater inundation there was. They just stuck with what happened on the known bodies of water. We have fossil evidence in North America of these tsunamis going across land and creating piles up of fossils. Well, with this research at the same time, other teams found areas where the ocean floor, which is now exposed in cliff fronts in Mexico, what was then the ocean floor was actually dredged order of 50 feet as this wave went through the world, literally wiping out life on the land and beneath the sea that was susceptible to this kind of a pressure front washing across it. The energy of this is just amazing to think about. And yet there was still life that survived through all of this to repopulate the world, showing that while we may be causing massive alterations to our world right now, life will find a way. We just may not be that life.
Right.
Dinosaurs
Yeah.
weren't that life.
So, I mean, do we know how big that wave got?
It measured over 2 miles high at its peak, according to these models. So twice the altitude of Denver.
Wow.
Yeah. Yeah, it would reach Denver. Yeah.
Yeah.
That's crazy.
Yeah.
Yeah.
So
It would drown Denver under a mile of water.
Yeah.
So the thing to remember, though, that you only really get that peak at the very first moment. It very quickly falls off. And the peak of the tsunami at that moment wasn't the most interesting part. The shockwave in general was flinging dirt, water, flora, fauna, very dead dinosaurs out of the atmosphere. So at that point, I don't think they were worried about the tsunami, and it very quickly fell off so that you were dealing with tens of meters in very short order. But it's still amazing to think about.
Now, we got some information on the biggest crater in the world. It's in South Africa, actually. Verdefort. How do you say that, Alan? Is that right?
Friedefort, yeah.
Friedefort? Okay. So it was believed that it was a 15-kilometer object. It's the biggest known crater on Earth. It's about 160 kilometers across, I think. And so people have done new research on this, and now they've upscaled the size of it. So now they think it was actually a 25 kilometer object hitting Earth. And the size of the impact crater is more like 180 kilometers across. So like there's parts that have been weathered that they just hadn't realized before. And this was 2.1 billion years ago. And so it was, and I forget, they just said it was like orders of magnitude more damaging than the one you mentioned.
Yeah. So that
was a bad day for Earth.
That was 3 times the diameter of the
Chicxulub, yeah.
Yeah. And things go, I mean, it would be the square of the diameter is the area that was carved out. That's a lot. So 9 times the area torn out of the surface of our world. This is your reminder that the earliest days in our solar system were not places you wanted to be. And over time, things have gotten better, but we do things like the DART mission to remind the solar system we would like to pretend we're in charge while we actually know our world is very fragile and a rock could come out from the sun at any moment and come at us.
All right. Speaking of asteroids, Nick. Oh, go ahead. Before we,
I was going to say that crater is so big. I drive across it regularly whenever we take the family on holiday, and you don't notice it. You just don't see it. You're crossing some mountains, and then you're driving through plains. It's yeah. You didn't even know it existed until satellites.
Is there like a museum, or is there like some kind of national park there that you can go to?
Not that I'm aware of. I mean, you can find it on Google Maps. The town that it's named for, which is on the dome, that I think is what's left of the central spike.
Interesting. All right, Nick, one last asteroid story.
Yay, asteroids. So this is a fun story. So one of the things that we see when we study meteorites is we see impact glasses. And often these impact glasses are very dark. But we don't see them super often. It's not every meteorite that we collect that's going to have impact glasses. Oftentimes the impact pressure is just high enough to do that. And so we weren't really sure how common this was in the solar system. Then the Chelyabinsk meteorite came by, and what we covered from the fragments of that were chock full of this stuff. But we didn't really know, like, okay, where could that come from in the solar system? So when we usually talk about space weathering, we're usually talking about the interaction of the solar wind with the surface of an airless body. And it's doing some interesting chemistry to the surface. It's breaking down mineral structures, freeing little bits of iron. And the effect that has is it darkens the surface. And it removes a lot of the mineral spectroscopic features. So you look at it and it becomes dark and featureless. But it turns out that's not the only process that will do that. This impact darkening, the shock process, will also do that. And so this was a story where a group of actually astronomers were looking at asteroid taxonomy. That is, how we classify asteroids. And one of the big questions is, all right, this is what we see spectroscopically. How does that relate to the hand samples we have, the meteorites we've collected? And they found one that they have very good evidence has a lot of the shock process having occurred to it.
So what's happening, do you think? Is it happening out in space, or is it happening as it's coming through the atmosphere?
This is happening out in space, very definitely. And what's going on is it's having a large impact that's sending a high pressure shock wave through it. You know, the kind of thing that Pamela delights in.
Right.
So they talk about the impact pressures required to do this. There's kind of 2 levels of the event, and it's really based around, you know, what sorts of things it starts to break down and what sorts of materials it forms. The low pressure end of this is 50 to 60 gigapascals. That's a lot of pressure. The high end of this is 90 to 150 gigapascals.
Also a lot of pressure?
Also a lot of pressure. For reference, when you're talking about the deep Earth interior, we end up doing experiments that get up to 5 or 6 gigapascals. And when you're getting down to the core mantle boundary, you might get as high as 20. This is a lot of pressure that's being formed in a very short period of time. This isn't just ambient pressure. It's what happens when two large bodies hit each other at a fairly substantial angle, or when a very large body pulls something down to it.
Can you work back the scale of the impact based purely on the shock that you see in the meteorite?
Other people can. I am not that good of a physicist.
When I mean you, I mean the royal you.
The scientific community can start to work that stuff back and say, all right, what sorts of body collisions? Now, it's going to be a range because it matters. Like, was there one very large object pulling in a very small object? Or is it two fairly large objects coming in at different orbital velocities? And it was a chance crossing orbits where they both happen to show up at the same time. So there's a lot of parameter space to work around that. And usually what we think about is how big of an object does it take to make a gravity well to hit hard enough to reach these pressures.
So cool.
That's
really cool. And I mean, like, we look at those rubble piles. We look at Dimorphos most recently. We know of Ryugu. We know of Bennu. They're covered in boulders, chunks. And I'm sure if you could get your hands on those chunks, slice them in half, you would see these shock crystals inside, and you could use that to start to peel back the story of what this poor space rock went through.
Yeah, I mean, you could really look at, if you could look at a lot of these rocks, what collisions were involved? Was this one body that got hit really hard and a bunch of debris came together and formed this object? Or is it an object that formed large enough to start picking up pieces from other collisions? What was involved here? Is it one thing? Is it many things?
Yeah.
I would love to go to an asteroid and pick apart that boulder field. I would spend a decade just happily looking at those things.
Well, and you could imagine that you could then start to figure out what the early solar system might have looked like just from the amount of impact that you're seeing in these rocks to tell you, if there was a lot, then the early solar system was more busy than we thought, or maybe it was less busy. You might even be able to see different times and chart the different bombardment periods.
Yeah, you can also start to look at things like how homogeneous was the solar nebula. Like, we know that Earth and Mars ended up very different compositions, and Venus was a different composition, and Mercury is a very different composition. Is that just because of what objects ran into each other that ultimately made these bodies? Or is it saying that this was a zone of the nebula and it was a feature of what it was formed in that made it that way?
Yeah.
We don't know the answer to that.
Really
and there's kind of two end members to the model. One's what we call quiescent, very peaceful early solar system where stuff just sort of formed and sucked up what was in its local vicinity, and there's your planets. And the other end member model is incredibly chaotic, where bodies ran into each other all the time. There are far too many to be stable. And so orbits changed drastically. Many things fell into the sun. Many things got flung out. And the bits and pieces, some of them survived and became planets. Others almost survived and became asteroids. And others gone, either in the sun or out of the solar system.
Right. All right. Well, we've reached the end of our hour, so it's time to things up. Nick, you were talking. What are you working on, and where can people find out more?
I'm working on a process to get at rare earth elements, which is something we really, really need for the green economy. Turns out I'm doing a second postdoc that doesn't happen to be space related. But if you want to check in with the fun things that I do from time to time, I still occasionally post to The Wandering Scientist on Twitter, on Instagram. One of these days, my website will be back together.
Alan.
Yeah, so the Urban Astronomer podcast is still up. It's urban-astronomer.com. It's mostly back catalog these days. I've also started writing at Universe Today, so, punt Universe Today. And finally, I'm
Good
on
site.
Twitter.
I like that site.
Yeah. Yeah, I just recently discovered it's quite good. And I'm on Twitter at UAstronomer, where I talk a bit of space, bit of tech, and a bit of politics.
Fantastic. Pamela.
I am extremely busy working on planning out, along with a whole bunch of volunteers, this year's CosmoQuest, a celebration of science and creativity, this year focusing in on that tech that is allowing us so much of the exploration we do today. There are many live events planned for our Twitch channel, but in addition to that, we are also going to have a ticket holders only Discord with a large vendor room where everyone is going to be offering either a discount or a free item with sale to ticket holders only. We're going to have a bunch of space related games and contests, and all of you are invited. Go to cosmoquest.org and get your tickets today.
Fantastic. Of course, I'm Universe Today at all the things. The fire hose of space content continues. So check us out on YouTube, on Twitter, and of course, our website. All right. We've reached the end of our hour. Thank you, everyone, for joining us today. Thanks, everyone, watching us on YouTube and on Twitch. Thanks to all the moderators. Thanks to Nancy Graziano for herding all the cats. We will see all of you next week. Thanks, everyone.
Bye-bye, everyone.
Bye-bye.